This line is about the storage location assignment problem, SLAP, specifically for reefer containers. Unlike dry containers, reefers are part of a cold chain. They require continuous power and temperature control, so where you place them is not only about cost or convenience. When the slide says cold chain storage location assignment under power and temperature constraints, that is the core reality. A single bad placement can overload power, break temperature limits, and destroy cargo value. Reefer containers require continuous power and active temperature monitoring. That means the yard becomes an energy and compliance environment, not just a storage grid. Placement must protect cargo integrity while still optimizing terminal efficiency. In practice, you are balancing service quality, safety, and regulations against travel distance, accessibility, and space utilization. In this scenario, Container Terminal Delta operates 24/7 and handles over 500 reefer containers per day. The terminal has 150 reefer power points distributed across 6 storage blocks. Cargo requirements can be extreme. Some shipments need deep cold conditions, such as -20 degrees, and any deviation can cause severe damage. So every assignment decision is also a risk decision. Peak seasons make the problem harder. Reefer arrivals surge by 200%. Power grid capacity becomes constrained, and the risk of overload or temperature deviation rises. The assignment must balance utilization, energy, compliance, and service quality. In other words, you cannot optimize just one metric without creating a failure somewhere else. This deck is organized into tiers. Tier 1 is a mixed integer programming formulation. Tier 2 uses the first fit decreasing heuristic. Tier 3 uses ant colony optimization. Tier 4 applies reinforcement learning with a double deep queue network. Tier 5 uses an integrated digital twin. Tier 6 uses an autonomous multi-agent ecosystem. Tier 8 introduces a value-aligned and ethical framework. Tier 1 captures assignment decisions and hard feasibility constraints. It includes power capacity constraints and temperature compatibility constraints along with costs. The goal is minimum total cost while avoiding unsafe placements and peak power spikes. Operationally, that means you are minimizing cost while keeping the cold chain intact and the electrical system stable. The sets define what objects the model reasons about: the set of reefer containers, the set of storage locations, and the set of time periods. Operationally, these sets define scope. If a container or location is not represented, you cannot enforce its requirements, so defining the sets cleanly is the first step to a model that can be implemented. Parameters represent the fixed facts the optimizer must respect. In this model, they include location power capacity, container energy consumption, assignment cost, dwell time, required temperature for each container, and temperature ranges for each location. Operationally, parameters reflect real constraints: how many kilowatts a block can support, what temperature bands are achievable in different areas, and what it costs to operate in each location. Decision variables represent the assignment choice, whether container R is assigned to location L. The model also tracks total power usage per location and activation decisions for locations. Operationally, this structure gives you 3 levers: where each reefer goes, how much load each area carries, and whether you open additional locations to spread load. The objective combines assignment cost, activation cost for using locations, and a penalty for peak power usage. Operationally, that last term matters. Power penalties discourage concentrating too much electrical load in one place, which is exactly what causes breaker trips and grid instability. Assignment cost reflects accessibility, handling, and operational priorities. Activation cost discourages using too many locations, which can increase complexity and monitoring overhead. Peak power penalty discourages concentrated electrical load. Together, these terms balance cost efficiency with power grid stability and operational controllability. The assignment constraint ensures every reefer gets exactly one location. Operationally, this prevents the model from solving the problem by leaving a container unassigned. For reefers, unassigned means unpowered, and unpowered means cargo damage. The capacity constraint prevents overfilling an activated location. Operationally, capacity is not only physical slots, it is also how many active reefers can be monitored accessed, and serviced without creating bottlenecks. The power constraint ensures the total electrical load of assigned reefers stays within the power capacity of each location. Operationally, this is a hard safety rule. Violating it can trigger breaker overloads, blackouts in a block, and cascading temperature violations. The temperature constraint ensures compatibility. Each assigned location must support the container's required temperature within its allowable temperature range. Operationally, this is cargo integrity. If a location cannot maintain the required temperature band, the assignment isn't feasible no matter how cheap it is. These constraints work together. Assignment ensures exactly one location per container. Capacity prevents overfilling active locations. Power prevents overloads and grid failures. Temperature ensures compatibility so cargo stays within required limits. This is why reefer slap is different. Feasibility is about physics and compliance, not just space. This figure illustrates an enhanced reefer container monitoring system. Operationally, monitoring is the enforcement layer. Even a perfect plan needs detection and response. Alarms, power telemetry, temperature tracking, and operator workflows that catch issues before cargo is lost. The concrete example includes 3 reefers. A pharmaceutical container requires minus 18 degrees at 45 kilowatts for 48 hours. Fresh produce requires plus 2 degrees at 35 kilowatts for 72 hours. Frozen seafood requires minus 20 degrees at 50 kilowatts for 96 hours. The slide reports that an optimal assignment yields total cost 65 units while respecting power and temperature ranges. The lesson is that feasibility and cost must be evaluated together, because a low-cost assignment is worthless if it overloads power or breaks temperature limits. Tier 2 uses first fit decreasing. It sorts containers by energy consumption in decreasing order, then assigns each container to the first feasible location by power and temperature. Operationally, this produces fast, near-optimal plans when problem size is large. It is a practical baseline for live operations, especially when decisions must be made quickly. This slide shows the first fit decreasing flow. Operationally, the flow makes the heuristic implementable. Sort by load, scan locations, assign to the first feasible option, and repeat until all containers are placed. This slide begins the implementation details. Operationally, pay attention to how feasibility is checked. You must check both power and temperature compatibility, not just one, or you will produce unsafe assignments. This slide continues the implementation details. Operationally, this is where repair logic often becomes necessary. If the first feasible placement later creates overload, the heuristic needs a reassignment step. The reported output shows a total cost of 847.2, and it shows a power overload at location 2, 105 over 85 kilowatts. Operationally, this illustrates the limits of a pure heuristic. A fast rule can produce a plan quickly, but it may need a repair step or a second pass to fix violations before execution. Tier 3 uses ant colony optimization. It builds assignments probabilistically using pheromones that encode learned desirability of container to location choices. Over iterations, the algorithm reinforces good choices and suppresses poor ones, improving solutions while respecting feasibility constraints. This slide introduces the probability concept for ant colony optimization. Operationally, probability is the mechanism for exploration. Instead of always choosing the cheapest local option, ants sample choices based on a blend of cost information and learned pheromone strength. This slide shows the ant colony construction graph for reefer assignment. Operationally, think of the graph as the space of all assignments. Each path represents a complete plan, and the algorithm searches for low-cost, feasible paths. This slide begins the implementation. Operationally, focus on how solutions are constructed and how feasibility is enforced during construction. If feasibility is only checked after the fact, many iterations will be wasted. This slide continues the implementation. Operationally, this is where pheromone updates start to matter. Updates must reward assignments that are both low-cost and feasible under power and temperature. This slide continues the implementation. Operationally, pay attention to convergence behavior. If pheromones become too strong too early, exploration collapses and the search can get stuck. This slide continues the implementation. Operationally, this is where stopping criteria and best solution tracking matter. In a real terminal, you often have a time budget, so you need the best feasible plan available within that budget. The slide reports 100 iterations with 20 ants. Best cost improves from 1,247.52 to 823.15. It also reports an improvement over the heuristic of 15.8%. Operationally, this shows what meta-heuristics buy you. Better solutions with manageable compute time. Tier 4 models assignment as sequential decision-making. The agent selects a container and a feasible location. Learning balances assignment cost, power violations, temperature violations, and utilization. Operationally, this allows adaptation to changing conditions, such as shifting demand and limited power availability. This slide introduces the reward used for learning. Operationally, reward design is a policy design decision. If power and temperature violations are not punished strongly, the agent will learn unsafe shortcuts. This slide shows a double-deep queue network architecture for Reefer container assignment. Operationally, double-deep queue learning reduces overestimation bias and tends to produce more stable learning, which matters when unsafe assignments must be avoided. This slide begins the implementation. Operationally, focus on the environment definition, how state is represented, which actions are allowed, and how constraints are checked. This slide continues the implementation. Operationally, pay attention to how experience is stored and sampled. The agent learns from repeated patterns of feasible and infeasible assignments. This slide continues the implementation. Operationally, this is where network updates connect decisions to long-term outcomes. The agent must learn to avoid myopic assignments that create future overload. This slide continues the implementation. Operationally, exploration control matters. You need enough exploration to learn, but not so much that training is dominated by unsafe random actions. This slide continues the implementation. Operationally, this is where evaluation checkpoints matter. You must check that improvements correspond to feasible placements. This slide completes the implementation sequence. Operationally, deployment requires stable inference, fast decision time, and guardrails that block unsafe actions. After 1,000 episodes, the average score rises from minus 1,547 to 748. Exploration rate epsilon decays from 1.0 to roughly 0.01. The learned policy outperforms random assignment and improves on heuristics. Tier 5 creates a real-time replica of the Reefer terminal. It links power grid, cooling, sensors, operations, and predictive analytics. The twin enables what-if analysis and automated emergency response. Operationally, that means you can plan for failures before they happen. This slide presents a digital twin system architecture for a Reefer terminal. Operationally, architecture is about integration. Power telemetry, temperature readings, and container status must be combined into one consistent view for decision-making. The twin predicts 47 reefers face power interruptions, averaging 3.7 hours. It triggers emergency protocols. 23 high-priority pharmaceutical containers are moved to backup power zones. Diesel generators support 15 frozen seafood containers, and 9 containers are expedited for departure based on thermal buffer. Operationally, this is proactive loss prevention. Reported metrics include processing over 2.3 million sensor readings per hour, maintaining sub-second alert response time, and achieving 94.7% accuracy in 24-hour failure prediction. It reduces reefer dwell time by 14.3 hours on average. Operationally, that reduction improves both service quality and yard capacity. This slide references simulation components. Operationally, simulation components are what allow the twin to predict. You need models for thermal behavior, power distribution, equipment failures, and operational workflows. Tier 6 uses a multi-agent view. Container agents negotiate for locations based on power, temperature, cost, and deadlines. Location agents adjust pricing and allocate capacity, and resource agents manage shared infrastructure and emergency protocols. The result is emergent coordination under peak demand. In the reported scenario, 85 reefers compete for 60 optimal locations. Within 4.7 seconds, agents form 3 coalitions: a pharmaceutical alliance, a fresh produce cooperative, and a standard freight collective. Emergent pricing enables voluntary load shifting and reduces energy cost. Operationally, this is distributed decision-making under scarcity. Reported outcomes include a 23% energy cost reduction through voluntary load shifting. 15 non-critical containers accept slight temperature variations for 40% cost savings. Utilization efficiency is 97.3% with zero temperature violations at 142% of standard capacity. Total operational cost reduces by 18.7% versus centralized optimization. Tier 8 adds governance. It encodes constitutional principles such as zero tolerance for temperature violations, and it adds environmental and fairness constraints. Operationally, the point is trust. Under scarce capacity, the assignment system must protect safety and public outcomes, not only profit.